Welcome student, welcome to Urban Pro. Today I am going to discuss electrostatic potential and capacitors. So electrostatic potential, what is electrostatic potential? See, electrostatic potential, uh, it is the work done. It is the work done by an external force to bring, by an external force to bring a unit positive charge from infinity to the point. So definitely I'm talking about electrostatic field. Suppose here in this region we have electric field produced by something, maybe charge, maybe anything. The electric field produced in this region, there is electric field. And now we wish to find the electric potential at this point. Let's say the point is P. How we have to calculate, how we have to find out the electric potential? We have to bring a unit positive charge, that is 1 coulomb positive charge, from infinity to the point P. And for that, the work done by an external force. Suppose I am bringing this one positive 1 coulomb charge. So here I am the external agency and I am applying some external force. I am doing some work. That work is the potential at point P. Okay. So now we will discuss the potential for for an electric field produced by unit for a positive charge. Let me write the potential in an electric field produced by a point charge at a distance r is what? Suppose, let me draw. Suppose this is the point charge Q. Okay, we want the electric potential, value of the electric potential or electrostatic potential at this point P, which is at a distance r from the charge Q itself. Okay, for that we have to bring a unit positive charge from infinity. From infinity means there the potential is 0, means there is no interaction with the Q charge, no attraction, no repulsive force. That point is known as infinity. So from this infinity we have to bring this unit positive charge to the point P. That work done will be the potential at point P in the electric field produced by this charge Q. Okay, so let us derive it. So the potential is denoted by V, which is nothing but the work done by the external agency or the external force. So how we will calculate it? See, work done, as you know, is nothing but the force dot F dot dr, isn't it? But here we have to integrate it, F dot dr, because at every point on the path when the particle or the charged particle was bringing, the force is variable. That is why we have to integrate it, isn't it? The limit will be, what will be the limit of the integration? It will be infinity to the position r. Okay, so see here, infinity to r, F dot dr is equals to integration infinity to r f dot dr. F means what? K q by r square dr. A negative sign will come. Why? See, the direction of the force by this q charge and the direction of the displacement is just opposite. That is why a negative sign will come. Now on integration, what we will get? Kq is the constant. Let me take it out of this integration. Finally, we will have infinity to r dr by r square. What is the integration of 1 by r square? We all know it is minus 1 by r, and limit is infinity to r. Also we have kq initially. So it will give uh, a negative sign. So earlier we had a negative sign. It will be a negative sign here, a negative sign, minus kq will be here. So finally we will have kq by r. So the expression for potential at a point at a distance r from a q charge, a point charge q, is kq by r. Now we will apply this. That is, we will see example. Okay. So what may be the example? Suppose the example we can set, suppose here this is, let me change the color. What is this? This is nothing but a square only, but at the vertices of the square few charges, point charges are placed. Okay, this and here also. What is the magnitudes of the charge? Let us take it as q1, q2, q3 and q4. What is the length of the, or what is the arm of this square? Let us L. This is also L, this is also L, this is also L. What is the question here? The question is, find the electric potential, or potential only, at the center of the square due to the given charge distribution, due to the given charge distribution. Okay, so here we have to solve it. Here 4 charges are there. We have to find the net potential at the center. This is the center. So V will be what? The potential will be due to the charge Q1 with the charge potential due to Q2, potential due to Q3, potential due to Q4. See, all the charges Q1, Q2, Q3 are at the equal distance from the center. So we have to find out what is the distance. What is the distance between the center and the charges? So for that, let us draw the diagram once again. So suppose this is the square. We have to apply geometry a little. What is the distance? This distance is L by 2. Now we connect this. This is the length that we are looking for from the center to the vertex, one vertex. This is L by 2. This one is also L by 2. So this is nothing but the hypotenuse, that is root L by 2 square plus L by 2 square. It gives root in denominator 4 and L square plus L square. So it gives ultimately root of L square by 2, that is L by root 2. So now we will apply here. So what will be the answer? It is K Q1 by the distance. Suppose I write it as D, and plus K Q2 by D plus K Q3 by D plus K Q4 by D. So K Q1, Q2, Q3, Q4. So I can take common K by D, then I will left with Q1 plus Q2 plus Q3 plus Q4. Now let me put the value of the D, as D is nothing but L by root 2. So L by root 2 and Q1 plus Q2 plus Q3 plus Q4. Now, if in any numerical example or problem, if the Q1, Q2, Q3 is given, then we can readily find out the value of the potential by just putting the value of the Q1, Q2, Q3, Q4 and the value of K. In SI, the value of K is 9 times 10 to the power 9 with the unit. Okay. So this is the application of this potential, electrostatic potential. Now let us check one more potential. I will find electrostatic potential for one more system. Okay, that is very interesting actually. Suppose this is what is this? This is a circle, and this is the center of the circle, and the positive charges are uniformly distributed over the circumference of the circle. So this is the circle. I draw it by black color, and the charges are positive and represented by this positive plus sign. Now we have to find, suppose the radius of this circle is capital R. Okay, so let me write the question. Find electrostatic potential, electrostatic potential at the center of the circle due to the given, not given, let me write due to the uniform charge distribution. Uniform charge distribution on the circumference of the circle. Okay, let us give me one more information, that is the total charge is suppose capital Q. Okay, now we will solve this. How to solve this? See, this is the circle on which the charges are uniformly distributed. Now we will see how the potential will be calculated. Okay, which one is the center? This is the center at which we are going to find the electrostatic potential. Okay, see, the radius is, this one is the radius. Suppose I take an elementary length on the circumference of the circle. Okay, and this is the elementary length and the charge. Suppose the charge is dq. This charge is dq, that is very small charge, that is dq. Okay, so what will be the potential at the center O due to this dq? Let us write it by dv. Nothing but k, the amount of charge dq, and by the distance r. So this is the potential due to the elementary charge dq on the circumference. Correct? but we are looking for the total potential at the center, isn't it? We are looking for capital V, total potential, which is nothing but the integration of dV. That is, we will just sum all the charge. We will sum all the will sum the potential at the center due to all the elementary charges, isn't it? We will integration of dV. What does it mean? It means we are taking the summation of dV. That is the potential due to all the elementary charges present on the circle. Correct. So how to find it? Now we will just write dV. We will replace the dV by as we find in the last line, that is k dq by r. Correct. So as you know, the k is a constant, so and the radius is also constant here. So we will take it out of this integration. So we are left with only integration of dq. What is integration of dq? It is the summation of all the charges. It is the summation of all the charges. This gives us only k by r is as it is, and the summation of this integration of this dq is nothing but the total charge q, which is given in the question. The total charge is q. Correct. So this is the expression for potential due to the charge distribution uniformly on the circumference of the circle. Now let me point out one point, that is, see, here it is written that the uniform charge distribution, but total charge is q. Now if we distribute this total charge q not uniformly, still the potential will be kq by r only. Why? The potential depends here only on the total charge q and the distance between the charges and the center at which we are looking for the potential, and the k, you know what is k, isn't it? So it doesn't depend on the whether it is uniformly distributed or not uniformly. Okay. Now this was example 2. Let us take one more example, that is, now we will find the electrostatic potential on the axis, of the circle, on the axis of a circle. That is, the circle will look like this is the circle. This is the same circle that we just discussed, but now our point of view is different. We are looking from different angle. That is why this circle is appearing like this. Okay. And now we will draw the axis of the circle. This is the straight line which is passing through the center of the circle and perpendicular to the plane of the circle. This is nothing but the axis, as you know. Okay. And definitely charges are distributed. Now I will not mention whether it is uniformly or not uniformly, because here there is nothing about the direction. So it depends on the total charge and the distance. So I am writing the total charge q. Total charge q is distributed on the circumference of a circle. Find electrostatic potential due to this distribution at a distance x from the center. So you know this is center O, and we want to find the electric potential at this point. Let's say the point is P, and the distance between the center and the point is x, as mentioned in the question. Okay. we have to find the electrostatic potential. So this is again a very simple question or example, whatever you say. So see, this is our, let me just copy and paste for the sake of the time saving. I copy it here, I'll paste it. See, the thing is similar. Now you tell me, here I'll take a elementary charge. Suppose this is the elementary charge and its magnitude is dq. Okay, I have to find the electrostatic potential due to this dq charge at point P. For that, what do we need? We need the distance between the charge or the elementary charge and the point at which we are looking for the electric potential. So this is the distance. See, if I take the distance or the radius to be r, this is the radius r, then what will be the distance? This distance will be, see, this forms a right angle triangle. Here the one length, one of the r is the one of the value and x is the another, and the hypotenuse will be definitely x square plus r square, isn't it? Now let us check, suppose one more elementary charge I take here. This is also at a distance root under x square plus x square from the from the point P. This is also at the same distance x square plus r square. Not only these 2 points, whatever be the point, at this point here also dq charges is there. This point is also at a distance root over x square plus r square. So as you can see, all the charges, all the elementary charges are at a distance root x square plus r square from the point at which we are looking for the potential, that is from point P. All the points are equidistant. You can check it. Okay, not only this side only, but the lower side as also, these points are also equidistant from the point P. So how to find the potential, net potential? For the elementary charge, the elementary potential at point P is nothing but k, the amount of charge q, and the distance, which is nothing but x square plus r square. But we need the total potential v, which is nothing but the summation of dv. Here, see, the distance root x square plus r square is constant for every charge, elementary charge. So we will take this k, we will take this x square plus r square out of the integration, and we will integrate dq only. What is the integration of dq? This represents only the total charge which is distributed on the circumference of the circle, isn't it? And the left, and the we will left with k by root x square plus r square, and a q is multiplied. Let me write the q here for clarity. Okay, so this is the potential at the at a point on the axis of a circle, and the charge is distributed like this. Here also this will be same for uniform as well as for non-uniform, for both the distributions. Okay, now we will discuss little about capacitors, electrostatic potentials and capacitors. See, capacitors, which is a device only. Capacitor, what is this? Capacitor is a device, which is used to store charge, Okay, we have multiple type of capacitors. Usually in market there are many types of capacitors, but we initiate the discussion using the parallel plate capacitor. Parallel plate capacitor, as the name suggests, there are two plates which are parallel to each other. This is a plate, and the another one is, I am drawing it. This is the other plate. These two plates are parallel to each other, and the combination of these is known as parallel plate capacitor. Okay, so parallel plate capacitor. Fine. The capacitor is a device, and one more term is there, that is capacitance. Capacitance of this, that is the ability to charge, to store charge. Capacitance C is nothing but C is equals to Q by V. Okay, C is equals to Q by V, and if we derive it, the expression for this capacitance, for this parallel plate capacitor, comes out to be A K epsilon naught upon D. What is that actually? What is A here, K here, D here? K is that dielectric constant, epsilon naught is the permittivity of the free space, and D is nothing but the distance between these two plates, and A is nothing but the area of these plates. Okay, area of both the plates. Fine. Now what we'll do is we will find the resultant capacitance of few capacitors when they will be combined in series and parallel, like we derived in the resistances. Okay, so see, here the scenario is just opposite to that of the resistance, so that is why I am not going to derive the expression for the capacitance in series combination and parallel combination. Rather, as here the case is just opposite, so it will be better if we discuss on the calculation of equivalent capacitance. Okay, so let me, before that, before going into the exact discussion, exact calculation of the equivalent capacitance, it will be better if I just mention what is the equivalent capacitance for series and parallel combination. So let me write equivalent capacitance for series and parallel combination. Okay, we are going to discuss this. So let me briefly tell you the formula. Let me recall you what was the case for, suppose this is a resistance and it is combined with one more resistance. Suppose this is R1 and R2. Then their equivalent resistance was, we write it as Rs to represent series combination. Rs is equals to nothing but R1 plus R2. This was the case for resistance, but we'll discuss for capacitor. See, here I have written the series in this blue color. That is why I am going to write the series combinations for blue using blue color only. Okay, so here we have a capacitor and we have one more capacitor. Suppose this is the C1 and C2. The capacitances of these two capacitors is C1 and C2. Then what is the equivalent capacitance when they are connected in series? Here the scenario is just opposite to the resistance. That is how we have to find here. It is just, as I am telling again and again, it is just opposite of this inverse of the resistances scenario. That is, this is equals to 1 by C1 plus 1 by C2. Okay. Okay. So this was the case for series. What is the case for parallel? This is nothing but, this is suppose one resistance, this is another resistance. We will connect them parallelly. This is the parallel combination. This is the parallel combination. Suppose this is R1, suppose this is R2. Then for parallel combination, 1 by Rp is equals to 1 by R1 plus 1 by R2. So this is that's how we calculate the equivalent resistance. What will be the case for parallel combination of capacitors? This is a capacitor. This is one more capacitor. We will connect them in parallel combination. Correct? Okay. This is C1, this is C2. So the parallel combination, the equivalent capacitance in parallel combination, it will be just opposite, that is C1 plus C2. Okay, so this is the expression. Now what we will do, see, just match it. This is just the opposite. Okay. Okay, now we will, what we will do, we will move on to the direct applications of these series and parallel combination. That is, we will discuss mixture combination and we will find the equivalent capacitance. Okay, so our heading will be mixture of series and parallel combination. We will give only one example. So suppose this is a capacitor. Here we have a capacitor. Here we have one more capacitor, and I add here one more capacitor. What are the points? Suppose this is point A, this is point B, this is point C, this is point D. The question is what? The question is find equivalent capacitance between A and D. Okay, so we'll solve it. We'll solve it. Initially, what we'll do, see, this is point A and this is point B. The capacitor in between this, okay, we have to give the values as well. Let the values be, suppose this is 3 microfarad, this is 2 microfarad, this is 2 microfarad, and this is 4 microfarad. Okay, so in between AB, the 3 microfarad will be as it is, but the in between the point B and C, as we can see here, there is a parallel combination of two capacitors, and as we discussed here, they will be just added as their capacitors and in parallel combination. So they will be just added, that is 2 microfarad plus 2 microfarad, that will, they will be 4 microfarad. It will be 4 microfarad. And between C and D, the in between C and D, there is one more 4 microfarad is connected. So now we will find, as we can see here, the A, B, these capacitors 3, 4, 4, they are connected in series. So the equivalent capacitance will be what? Not resistance, the equivalent series combination. How to find? This is 1 by this 1 by 3, 1 by 4 plus 1 by 4. What will give? This will give 4 times 3, that is, here it will be 4. Okay, we can write it in other way as well, like we can write it as 1 by 3 upon 2 by 4. Okay, so here 3 times 4, 4 plus it will be how much? It will be 6. So 10 by 12. So the equivalent capacitance will be what? The equivalent capacitance will be 12 by 10, that is 1.2 microfarad. Okay, I hope you all understood these concepts. If you till now have any doubt, then do contact through my Urban Pro profile, and see you in the next session. Okay, thank you.